here. Good afternoon. Thanks for coming. All right. So I was just setting up and introducing the quiz questions. So it looks like people were really happy about having the opportunity to complete more quizzes. I got several, but I haven't graded them. They're just going in my grading pile, unfortunately, because I am, as I explained, the director of my department and I am doing my secretary's work. So it is really keeping me busy, but I'm hoping on the weekend and getting organized, but you should have a sense when I give you the answers whether you did well or not, right? And it's no harm for you guys to keep sending me solutions. So next week is going to be, I'll give you another quiz, another set of 4 questions. Yeah, you'll get, well, 4, yeah. Because you'll get probability, the bin, the SDS, and the inference. I'll give you all those problems. And then that will be, next week will be our last week for the course material, but I'll continue answering your questions. I really want to focus on your questions after I show you what I want to show you. I'll probably finish earlier than Thursday. So by then we should be able to work on the final exams together. I'll discuss the distribution. You can work ahead on your own because now I've given you all the material. If you finish the notes and you can start working. You have time. You can start working on the review problems. I set it up in the calendar. In the schedule for the class. To be clear, I mentioned that the following week I will ask you for that weekend to prepare the mock exam. It's just it's a mock-up. It's laid out just like the final exam, so you have a feel for the kinds of questions that will be on it, and I've included the same distribution of questions, right? So from the inference unit, for instance, there's going to be 40% of the questions. So I've weighted the questions in the same way in the mock as the final test. So just you're supposed to prepare the mock yourself, and you're supposed to ask me if you have problems, and I'll share the answers and answer your questions from then. So starting next week, I'm going to be asking you to give me questions just like we did for the midterm. I think that worked very well. So you're going to be leading me around as opposed to the other way around. And then the final exam I will post on May 21st. May 21st is going to be the Thursday, so the class time. Well, it's not officially class, but the exam time. I never heard from anybody that they have a problem with that date. Let me know if anyone has a problem with the 21st. Okay, you can email me about that. So hello everyone. So let's work on this together then. We'd like to estimate population proportion. We take a random sample of n individuals and calculate an 80% confidence interval for p. And here it is, 0.33 to 0.37. Using the same sample, compute the 99% confidence interval for p. Okay, so what does the confidence interval give you? For the proportion, it gives you the point estimate, so the best guess at the population proportion is the sample proportion, and then we get the Z star, so many standard deviations away from the mean, and standard deviations are denoted like this from the theory that we discussed, and number two on the formula sheet, right? So the deal is that we are going between 0.33 and 0.37. So that's a width of, so this is the width, is equal to 0.3, it's very tight, 7 minus 0.33, so it's between 33% and 37%. So that's 0.04. So that's the width. If the width is that, then the margin is half of that. So the margin is equal to, or I'll just use the letter M. You should get used to seeing M. So M is equal to the width divided by 2, right? So, anybody get this? Anybody do it this way? So this is 0.02. And so that means that this thing, being the margin, must be 0.02 or 2%. I have to keep all this, the information in the question visible. So that means 0.02 is equal to, for 80% confidence interval, get me the Z star. Someone get me the Z star and put it in the chat. And it will be P hat 1 minus P hat. I really want to fit it in there. So make this bigger. I'm going to use this weekend to practice with my new stylus. It's supposed to be arriving today. Let's see if that happens. Okay. So the Z star, get me the Z star, and I'll put it here. So, well actually I don't even need to put N in. I can just put what N is. What was the N? Let's read the problem. N was a sample of, oh, just N. Okay, that's all right. That's going to be fine. I'll show you why. So someone gave it to me, 1.282. So 1.282 is a Z star. Is that correct? For 80%? Yeah. Yeah, because it's smaller than, like, yeah, you know, right, 80%, because one standard deviation is 68, so yeah. All right, so what do you see here? What I see is, I don't really need to calculate any of that. All I want to do is find out what it is. So how do I find out what that is? This whole thing is actually just 2% divided by that. And then I can use it in the next exercise, or the next part, to change the Z star, right? The level of confidence corresponds to a different critical value. Use the same number as here, and I could solve for what the margin is. Let me make sure if I'm thinking through this. Let me see this again. Oops. You're going to say compute the 99. Yeah, that's all we have to do. So, so Z star for 99. Well, actually, let's finish this. So what I want to do next is estimate this. And what is this? This is called the standard error. I can use a symbol for that. If that bothers you, don't use it. But the symbol for that is like this. It's the standard error, the standard deviation of the sample proportion. It's the it's the estimated one. So I have to put another hat on. So if that's really ugly, you don't like that, that's fine. Just leave it like that, like as a box. So that is going to be equal to can you see that? So the standard error, the box, is equal to, I'll put it in words in case you can't understand what I'm saying. So standard I'm having some delayed sensitivity, standard error. All right, and as I mentioned, if you get bored, just speed up the pace of the video using the settings on the bottom right of the screen. All right, so that's what we're going to calculate. So what do you get? 0.02 divided by 1.282. Sorry. What did you get? Did you calculate it? So essentially that's the value I'm going to use to estimate the next interval. So it's the standard error of p hat. So round that to 4 decimal places. Whenever I work with p hat, I round to 4 decimal places, or this can get really messy really fast. So that is actually going to be 0.0156. Let me do that again. Okay, so that's what that is. So that means now my goodness, all I want is a period there. Okay, now let's make the interval for 99%. To make the interval for 99%, we're going to, we still need p hat, don't we? Right, we don't need p hat because I just want okay, so we still have to find p hat. Right, 0.0156. So we still need to find p hat. So, what's p hat? Do you guys know what p hat is? If p hat, okay, I'll have to just write it out for you here. So, you understand that the lower limit, we just need to use one of them. The lower limit was p hat minus that margin 0.02. 0.02. That's equal to the lower end, right? The lower end was 0.33. So p hat must be, well, the other way to do it is just divide add them together. Okay, let's do it that way. Let's do it that way. Okay, sorry. I'm going to come up with another way. To find p hat, what's p hat is the question. P hat is in the midpoint of the confidence interval. So to find a midpoint, you know the midpoint formula, I hope. Well, if you don't, I'm going to show you. The midpoint is where you take the upper plus the lower and divide by 2. So the upper limit plus the lower, or you could do in the other order, divided by 2. That'll give you the midpoint, and that's what p hat is, okay? Because it's evenly in between the two. And I think that you can remember that better. You can tell me. Okay, so that's going to be 0.33 plus 0.37 divided by 2. Was this hard? 0.33. It's not hard when you see the answer. If you understand the interval, the idea of the interval, I hope now you understand it. So 0.33 plus 0.37 divided by 2, that'll give you the value of p hat. So it's evenly between those two. Is 0.35, right? I didn't have to do that if I understand that. So this is 0.35, so that's p hat. So we have p hat, right? So we have p hat, we have the standard error, and we know that the 99%, you gave it to me, Maylin, right? So the 99, so z star, so we have all the pieces. Let me circle the pieces. So this is p hat. This one is the standard error part, so that's easy. You don't know n, so you have to do it like this. Okay, you don't know n. If you knew n, you could calculate the standard error yourself, but because you don't know n, you have to do it this way. And then the z star, we have that, so I'll put it here. Z star, you can write this. You don't have to write all the details. I know which question you're answering, but you might like to do it for yourself in case you get confused. 2.576. So those are the three parts. Okay, put them together and tell me what the interval is, and let me know who got this yesterday. I guess it was a little challenging. When you have your notes and nothing is done this way, I guess it could be confusing, but now that you know how to do it, you could probably do it. Sorry. I hope you learned something though. So these are the gymnastics of the interval. These are the components, how to separate them, how to put them back together. Okay? So put it together and tell me what are the limits, and give me the interval. I'll give you a couple minutes. So if you work with my notes, you know you can express the interval this way. But actually, this is not complete enough. This still requires some calculation because you haven't combined these two. All right, so at least let's put the margin together. So this part is 0.0402 plus or minus 0.35. And then I guess, yeah, you could drop the other part, but because it's an interval for p, I prefer 4 decimal places. I'm going to keep 4, okay? So it's 0.35 minus 0.0402. Yeah, you rounded it nicely, Delia. But I'm going to keep it like this because of my rule for proportions to use 4 decimal places. So this will be 0.3098, comma, and 0.3902. So it's a wider interval, right? We expected that. We expected that because it's 99% confident. The other one was only 80%. So this is a wider net to catch the true population proportion, and this is going to be accurate 99 out of 100 times. 99%. Very good. So that wasn't so bad. So very good. Okay, let's see. We should, I'll save it. And go to the next question. Oh, I asked you to state the central limit theorem. So when I asked you to state the central limit theorem, unless you have a question for me, I'm going to go on. So when I asked you to state the central limit theorem, you can do it in words, but essentially what you have to tell me is, but we should all follow the 4 decimals even though the original interval only had 2. Yeah, Maylin. I mean, it's kind of a convention that whenever I use proportions, I use 4. So it's a good habit to have. But in the end, if your options, because you're going to be choosing from options on the test, well, then I'm going to give you, you'll see that there'll be some short answers you have to provide, like you have to solve problems. Okay, let me be more clear. So there's going to be a multiple choice section on the final exam, and there's also going to be one where you solve problems and show me your work. So in either case, it's a good habit for proportions to use 4 decimal places. If you have, if you're solving problems where the data was given to you or the original statements of the values were with 2 decimal places, I usually ask you to add 2 more, right? So it still fits within both paradigms. 4 decimal places for proportions makes sense. Okay, yes. So this is the answer here, just to let you know. So either of those, well, no, I want this answer, actually. And when I ask for an interval, I want the complete answer. But you'll see, so for some multiple choice questions, they'll just have you pick from options that look like that. Okay. So the central limit theorem. So what you need to state here is that if a variable, sorry, I did that wrong already. So if you know about a variable and you know its mean and standard deviation, population mean and standard deviation, even if you don't know its shape, provided n is greater than or equal to 25, the sample mean is approximately a normal shape, so it's regular and predictable, using the standard normal table, with the same mean but a standard deviation that's smaller because the sample means are all closer to each other than the original values. And it's smaller by a factor of 1 divided by square root of n. Okay, so that, I'm happy with that. That's the statement of the central limit theorem. You can do it more wordy than that, but yeah, that captures everything you want to say. And you could repeat it in the words that I just said. That would be fine as well. If you have any questions, well, I'll see how you answered that and let you know when we talk next. So you should have done this all right. Oops. There are 4 patients on the neonatal ward of a local hospital who are monitored by 2 nurses. Suppose the probability at any one time of a patient requiring attention by a nurse is 0.3. Assuming the patients behave independently, what is the probability at any one time that there will not be enough nurses? Okay, so this feels like a binomial. It looks like a binomial. Let's see if it has all the elements of a binomial. So x, n, p, k. What are we interested in? These patients. So the patients are the subjects. And we're interested to see, so I guess they're babies. They're neonatal patients. And there's only 2 nurses. So doesn't this already sound familiar? And there's only 2 nurses, but you have to separate out from that and the patients, but there's 4 patients. So I could put this in terms of the patients that I'm looking to see if they need a nurse to attend, requiring attention, okay? Requiring attention. Thank you, Delia. I'm doing my best. I'm getting better at this. Thank you for your patience. Okay, requiring attention by a nurse. So that looks like that's the P part, right? That's the success, probability of success, requiring attention. So success is requiring attention. I'll just put it here. Attention, requires attention. And so either none require attention, 1 requires attention, 2, 3, or all 4 require attention. There's 4, and the chance of requiring attention is 30%. And I'm interested in answering this question. So the last sentence gives me the problem. The last sentence gives me the problem. Assuming the patients behave independently, any one time there will not be enough nurses. Not be enough nurses. So there will not be enough nurses if, because there's only 2, that's the other important piece of information. There's only 2. So if more than 2 require attention, that is what I'm interested in. So 3 and 4, I need to calculate those probabilities. So let's get those and add those together. That's what we have to do. How many did that? This is familiar, guys. This is I think these are actually the same numbers as the one that I put in the notes. So I want to add these together. And, I'll do one at a time. So this one is, well, I guess I'll put that. So, how many ways out of 4 are there of seeing 3 successes times the probability of success times the probability of a failure? But there's how many successes? 3. That leaves 1 failure. Okay? And then for this one, it's going to be how many ways are there of seeing 4 successes out of 4? So 4 successes. So the probability of success to its power, and the probability of failure, none. And remembering, let's simplify a bit, the number of ways of seeing 4 out of 4, whenever it's and choose K, they're the same number. This is always 1, and this will always be 4. Well, not always be 4, there'll always be, how do I explain that? This one will always be N. So there's going to be 4 different ways to see 1 failure, okay? Because it's 3 successes or 1 failure. I explained that way back. I won't do it again here, but look back at your notes and watch the videos again to see where I show you about that, just to simplify the exercise. And then this one is also 1. So you should be able to punch that in your calculator without too much trouble and get your answer. So I get 0.0756 plus 0.0081 . So you have 0.0837, and that's the answer. So funny that I can extend my whiteboard like never before. There's always a running joke about having an infinite board to write on, and now I kind of do. Okay, so how do you do the 4? Do the times 4. Okay, so on the BA2 plus, to enter this, I'm going to enter it. I'll do the whole thing if you're going to do this on the calculator with the symbols and not do the short, the simplification. So you say 4 second function NCR. So you're going to write 4 second function NCR 3 then say equals, and then times, and then 0.3 y to the x 3 times 0.7 equals. That should give you the answer. And those are just the symbols. Okay, try that and let me know if you get my numbers. Did I make a mistake? Let's do this again. I think I used 0.03. No, I got it right. Okay. Okay, so 0.3 y to the x 4 is 0.081. So the y to the x is the power key. And you don't have to use the second function key for that. It's right above the 9. Okay, so that is the answer. Did I get the final answer? Yes, I did, right there. 8%. So it's an 8% chance that there's not going to be enough staff to attend to the child in distress, a neonatal birth. And so manager would probably have to put someone else on staff, or at least someone on standby, or what do they call that when the doctors are what do they call that when the doctors, it's okay. Anyway, on call. It's called on call. That's what they call it. The doctor's on call, or a nurse is on call. Okay, so that is the answer. Next. So this one I didn't attempt. There's always a wild card. I pulled this up. Okay. I wrote it in here, but I didn't prepare this. So let's see. Make sure I didn't make any typos. The following 5 games are scheduled to be played at the World Curling Championships one morning. The values in parentheses are the probabilities of each team winning their respective game. In a sports game, the favorite is the team with the higher probability of winning, and the underdog is the team that is less likely to win. What is the probability that at least one underdog wins their game? So the underdogs, let's circle the underdogs. That's an underdog. That's the underdog. That's the underdog. Oh, is it always on the left? They write it that way, okay. So the chance I didn't think about this yet. I have to think about it. Well, I guess we have to do some adding, because so I'm going to stop this one because I haven't thought about this. I really didn't. I stumped myself. I'll post this answer after I've thought it over, because this is not a binomial, because each probability is different, right? So if these are underdogs, the chance of an underdog winning here is different than the probability of an underdog winning here, and different than a probability of, like, they're all different. So each subsequent game has a different probability of the underdog winning. So it's not a binomial. So that's important to note. And I guess I'd have to consider all the combinations. So how many of you answered it as a binomial? It's not a binomial because the probability changes each time. All right, so I'll write the answer out and I'll share that with you. I'll send it by email, all right? Because it's going to look, it's painful watching me write that out now, and we were wasting time. What else did I have? Is that the last one? I think that's the last one. So I did them all, but this one, because I'll have to present you the answer. All right, it's not binomial. That's the main thing. So what I did was I took that question from an old exam, and probably one of the answers said this is not a binomial problem, and I didn't look at the alternatives. All right, so I want to continue with inference. And don't hate me for that last problem, please. I will do my best to give you part marks for that if some of you completed it. Not too many tried it, but some did, so I'll try and be fair. All right, so I left off with the question. Oh yeah, I left off with the question here. Okay, so this was the formula sheet that I asked you to print and keep it beside you, and then reprint if you need to, because you're adding comments and formulas to it, so that all the important formulas and information are available to you when you write the final test. And you need to start practicing now, right? Because the final test is 2 weeks away. So the question was, why can't I just like I did for confidence intervals when I don't know sigma, I used S as a substitute for sigma as a second best alternative, and I used T instead of Z. Same thing with the hypothesis test. I get a T statistic rather than a Z statistic, and substitute S for sigma. I'm just seeing Caroline's answer. Okay, so I'll check out what you did, Caroline, with the probability problem, and I'll send you guys the answer. So the question was, why is nothing here? Like, this is really blank. And I said, why can't we just solve n this way? So let me erase that just so maybe it's a little cleaner. So this is what you have. There you go. So there's nothing there. And I said, well, why can't we just do this? N equals Z star S over M squared. Why don't I just, repeat just like it did in the other formulas? So what's wrong with this? I asked you to think about it. What did you come up with? Any comments? No comments? Okay. Well, the reason is because you have not completely isolated for n. Okay, n is not completely on the left. Look here. Oh, sorry, I have to take, this is not z star. I'm going to substitute. First of all, let me fix that. Why can't we put t here? That's what I was trying to say. You haven't completely isolated for n. You have m here and t star here, like the z star and the m here, but the problem is that you've substituted s instead of sigma, but s has an n in it, right? S is the square root of 1 over n minus 1 summation, right? xi minus x bar squared. It's very messy, but there's an n. That's the point. There's an n here. So on this side, there's an n. So you can't solve, you haven't solved for n, which was the whole point. So rather than an analytical solution, right? Like this is known as an analytical solution, isolating n on one side, using other variables that you can obtain on the right-hand side. The problem is that you have an n inside on both sides. So instead, this can be estimated by using a computer, like even a spreadsheet, and just iterating, picking n and trying them and seeing if you can balance the equation. Okay, so computers can do it, calculators, I mean a human can do it, but it's much more efficient on a computer to solve something like this. So you don't have an analytical solution like you do in these two above. All right, got it? So basically you will not be able to isolate for n. So you'd have to do it a different way, and I'm not going to get into that. But you could do it, but not for this class. All right. Let's get back into it. So we're going to work with inference on a mean, just like we did up here. It's going to be inference on the population mean. In this case, the mean is unknown, and sigma is unknown. That's different from here. Okay, so I left you with the problems, it was about dog weights. That's where I left off. And I said you guys should work on it, and I just have a feeling you probably didn't. So let's see if we can look at that together. We'll find out if you did it. All right, so here. Let x denote the weight of a certain breed of dog measured at the age of 3 years. It is natural to assume that x follows a normal distribution. This is a simple random sample of 5. And then I worked through several steps. We're going to assume that we don't know mu and sigma. I didn't say it anywhere here, so there's no information in this exercise about the population. It just mentions a sample and the results. You see, there's nothing else. So this is more realistic. This is how we see data. We take a sample about something and we just plow forward, go ahead, and try and make inference about what it could be. All right, so let's go step by step. Calculate the mean and standard deviation of these 5 weights. All right, now just to remember, let's remember we know how to use our calculators for this, right? It's only 5 values, but for the mean, you know, you could just get the answer easily, but for the standard deviation, it's not so straightforward. So punch them all in, and don't look at the answers on the next page. Give me the answer after you've punched them in your calculator and tell me what you get. I'll give you 2 minutes. Okay, what did you get? So you should be entering into, if you have the BA2 plus, you're using the arrows, right? And you enter second function data, and you enter the values 10.9, enter down, and there's no Y value. 12 points, so you just go down again, 12.6, enter down, and 10.2, enter down, 15.2, enter down, and 11.1, enter down, and erase whatever you don't want, because I have extra values in there. And what did you get? I have a lot of data here. So what did you get for the mean and standard deviation? Nobody? Nobody yet? So x bar is 12, and s on your calculator is 1.991, keeping 2 more decimal places than the original numbers. Okay? So what's the standard error? The standard error, remember, for the sample mean, remember the theory from our formula sheet. Theory says x bar will be, in this case, approximately normal with a mean of mu and a standard deviation. Wait, I have to be careful. So for this case where we don't know about sigma, we don't have information on sigma, and we have a small sample, we're going to use t instead. So it turns out that just like when we, from the central limit theorem, I'm not going to put it here, I don't want to confuse you, we would write sigma over square root of n was like the new standard deviation. Now we don't have sigma, so the new standard deviation we're going to use is going to substitute that. So what is it estimating? S over square root of n is called the standard error because I don't have the actual sigma, I'm going to use s instead, so it's a estimate in itself inside of an estimate. So that's why we gave it the name the standard error. And it approximates, so this is actually like, it has a hat on it, which I don't get into all this notation because it can get confusing, I guess, but s over square root of n is approximating this. All right, so it's trying to be the real standard error, or the real standard deviation of x bar. I have the answers on here, and this is what I said. It approximates the standard deviation of x bar as sigma over root n, and that's its parameter, right? The standard deviation, the whole thing. I mean, this whole thing is the standard deviation of the sample mean. All right. So that is equal to divided by 12, square root of 12, and you get $1.991 divided by 12 square root, or 12 square root, flip it with the 1 over x key, times 1.991, and I get the number 0.5747, and I stop at 4, I think, or 7.848. and okay, so that's the standard error. So that's the standard deviation of x bar. How many degrees of freedom does the distribution of x have? X has n minus 1 as the degrees of freedom. So it was 12, so now it becomes 11. So with that information, we know to go to the 11th row. If we go to the 11th row, we want to pick up on the t table, because t has a distribution with 11 degrees of freedom. So we want to get the critical values from the t table for 90, 95, and 99% confidence. So we'll pick those up. So you go down, you go to the table, right? And you go for 90, 95, and 99. All the way to the 11th row, reading from the bottom up. 90 is this one. 95 is this one. And 99 is this one. Okay, so those should look familiar when I go back to the question paper. We're going to use those. So notice I went from the bottom, okay, to avoid confusion, because the top has probabilities, but those are only half. They're only the tail, upper tail probability. The confidence interval is what I want. Critical value for the confidence interval. So when I look at my answers, you recognize those numbers. Oh my gosh, what did I do? Oh my gosh, I screwed this up. I think I'm too tired. So n minus 1, nobody said anything either. N minus 1, n is not 12, n is 5. So that's why I got this wrong. Okay, I'm gonna have to force an edit. I'm gonna have to forcefully edit this to avoid confusion. This is not 11. This is I'll just put it here. This is not 11 and was 5 minus 1, so this is 4. And we're going to the 4th row, not the 11th row, so let's repeat that. Going to the 4th row, I apologize. 4th row, I'll put them in blue. So we want the 90th, the 95th, and the 99th. We're close to the top, so you can see here, right, that for the 90th, the upper tail is 5%, right, because the upper is 5 and the lower is 5, so that's 90 in the middle. For the 95, it's 2.5 upper tail, because 2.5 in the upper, 2.5 in the lower, so 95% in the middle. And similarly here, for the 99%, confidence interval corresponds to an upper tail of 0.005, with 0.005 in both tails. That leaves 99% in the middle. Okay, so those numbers should be familiar. So when I go back to the problem, And I see here I use this notation. You don't have to go for the notation, as I always say. Just let me know. Even the formula, I don't really need to see. What I need to see is the answers, the numbers inside of the formula. But anyway, usually we do like to write out where we're going with this. So I put them all together. The mean, it's always the same, right? This is the standard error, it's always the same. The only thing that changes is the confidence level, so the critical value changes. And you should practice computing this, like it's all here, but you should practice just so there's no confusion when you have to do it in the quiz or a test. And those are my intervals. And the last exercise is a hypothesis test. Test the hypothesis that the dog's weight, the dogs weigh 14 kilograms against the alternative that they weigh less than 14 kilograms. So the hypothesis there, so we're gonna lay out first the hypothesis, make sure we get that right. We're gonna carry out the 5 steps of HAPC if we have to. The only time we don't have to do the 5 steps is when I don't specify that you have to use the 5 steps. Or I ask you to, because it's a 2-sided test, you can use the confidence interval and test if the hypothesized value is contained within the confidence interval. If it is, then you haven't found anything special or radical as a result of your study. So here, remember, I have to decide first what kind of test it is. I know it's a test on means. Whatever number I put here, I have to carry it here. It's always an equal sign in the top. So all of this is the standard. The only thing I changed was the parameter. You have to decide what kind of test you're doing. This is a test for means, because I'm looking for the mean for weights. All right, so it's 14. 14 is what the status quo belief is. And I want to know, so whatever number that I put above, I put below it. And now I want to know, do we have evidence against it being 14? In fact, do we have evidence that it's larger than 14? Oh, sorry, less, way less. Less, not larger, less. So that's a less than sign. Now thinking about it, we had an X bar of 12, so that's already less. But is it, is 12 different from 14 given the variability of this variable, given the variation of this variable? Or is 12 and 14 the same, pretty much the same number, given the numbers don't spread out too much? So that's what we need to test. So we're going to look for how different these are in terms of standard deviation from the mean of 14. So what I'm going to do is doing the next step. The next step is, so I have to use the 5 steps because it's not a 2-sided interval, a 2-sided test, it's just one side. So I have to do the the next step. The next step is assume, what are we assuming? We assume H naught is true. It means that we're assuming that the true mean is equal to the hypothesized mean of 14. And as a result, then, it is the case that when we assess the evidence, so when I solve problems without the standard deviation when I don't have the population standard deviation and I have to use the t-test. I somewhat combine assume and assess, just because it gets really wordy otherwise. So we're going to assess the evidence. And we're going to say that t is equal to x bar standardized by the hypothesized mean and divided by the standard error, which is s over square root of n. So we're not so familiar with the t-distribution, right? We've been practicing a lot with the z-distribution, so we usually just carry out these steps, and we get a better feel. You get a better feel for the t-distribution as you go, but because we always change the level or the row that we're looking at, because the sample size changes, it becomes a little difficult to be able to just eyeball it and say, oh, well, that is an outlier, that isn't an outlier, because outliers, just because it's laid out differently. The t-distribution is more flat, right, when the standard, when the sample size is low. All right, so what I need to do is compute this. This is 12. The hypothesis one is 4. S was 0.89. I just rounded it to 2 decimal places in the end for this exercise. And then divide that by the square root of 5. So be careful with entering this to your calculator and make sure you can get the answer. So it seems like a large number. I'm gonna look at my neater notes. We don't need this because we already did this, right? That's what I have to fix. 0.89 was already the standard error. It was already what we divided by. We already had this as 0.89. Okay, so we didn't need to do the divide by root 5. And yeah, I felt like I was going on overdoing things. All right, so then when you compute that, you get .247. So just be careful. I standardized 12. And I get negative 2.47, and the issue is, so is it an outlier? Do we consider that an outlier for our t-distribution? We're going to compare that against t4, right? So we need to see, is this is low, it's less than, but is it significantly lower? So we're going to translate this number into a p-value, and from the p-value we're going to interpret. Remember, the p-value is the probability of seeing such a result as extreme or more extreme given the hypothesis is true. So what we're essentially going to do is see if this 2.47 falls in what we call the rejection region. So I made a drawing here, but I'll draw it freehand. Actually, I left some space on the next page. I left space for it. I laid out all the steps. I combined 2 and 3, assume and assess, and I want to calculate the p-value now. So the value that we got was negative 2.247. So I'm going to plot it. Okay, that's what you do. You take your t-stat and you plot it. T-stat is equal to negative 2.247. And I want to check what's the chance of having that outcome, where this is the 4th row, and I've assumed for this that the hypothesis mean is 14. So, or I assume the true mean is 14. So I have to go to the 4th row and look for that number. Now remembering the rows only have positives, so what I'm going to look for when I go looking is I'm going to look on this side. And find that, and then I will say that that and that are the same thing due to symmetry. Can you see that? So let's go look for that number, 2.247. So I'm doing all of this because nobody told me what the population standard deviation would be. I have no information on that, so I'm going to use the t distribution, 4th row, 2.247. It looks like 2.247 is in between these two. This corresponds to an upper tail probability of between 2.5% and 5%. Do you see that? So that's what I'm going to write down. So the answer is that the p-value, I've done all this drawing, and I just have to say the p-value is between 2.5% and 5%. Okay, that's the answer. It's messy, but it's nicely written on the next page. So between 2.5% and 5%. So that is actually in the rejection region, right? It's small. It's less than or equal to 5%. So it turns out for a T4 at 2.247, you are going to be an outlier. That corresponds to an outlier. Let's look back at that T-table. What else would be considered an outlier for a left-tailed test or a right-tailed test? See if you understand what I'm getting at. So upper tail 5. So all these values here, you see all these values here? For a one-sided test, all these values would indicate that you would reject. So you see, it's not just like 3 standard deviations like it is for the z-test. So 3 standard deviation using the normal distribution will be an outlier for sure. I mean, that's the cutoff that we use, right? And then we get more specific and we say 1.96 if it's a two-sided test. If it's a one-sided test, we say 1.645, right? Yeah, I don't know if you know what I'm talking about, but we say if it's if we allow for 5% to be our level of significance, and we have a one-sided test, and it's a situation where we're using the z-stat, we actually know the standard deviation of the population, then at 1.645, if it's a difference of 1.645 standard deviations from the mean, then we would have rejected the null hypothesis and say we have a significant test result. We have something new. We actually found evidence against the null. If we have a t-distribution, however, depending on the sample size, it's all these possible different numbers, right? All these possible different numbers here. So in our case, at 2.13 to after 2.13, you have 5% in the tail, and that's what we're going to say is enough. It's strange enough that the outcome that we got is indication that we can reject the null. We have evidence that, in fact, the sample came from some other type of distribution, not a distribution with a mean of 14. Something smaller, rather. Okay. If you didn't understand what I said, that's okay. I'm trying to just expand your comprehension, synthesis. But really, all you have to do is finish the question by concluding now. In the concluding step, it's always the same, no matter if it's a one-sided test or a two-sided test. We always write p-value. This is distracting. So I'm going to say conclusion p-value. This is what I expect you to write. Less than or equal to alpha means reject. Now fill it all in. So that's that test. And that's for that we reject H naught. So we got, our answer was between, and I'm going to write it as a B/T, between 2.5% and 5% is smaller than 5%. So we do reject H naught. We did find something fantastic and new. We have evidence to suggest that the weights are less than 14. So we can write it in words. The test is significant. That's one way to say it. Another way to say it is we have found sufficient evidence to suggest that the weights or the weight of a dog is less than than 14. we have found sufficient evidence to suggest that the weight is less than 14. So we have evidence, okay? And as it is, this was just one study. Maybe someone else will conduct another study and come up with a similar result, and maybe some other studies will be done that come up with different results. In the practice of science, usually one study alone doesn't cut it, okay? So that's why we say, we never say that we've definitively found anything. We just say we have evidence, okay? When people make statements like sounding so confident in their results, maybe they've looked at several studies at once. They've combined them in what I mentioned to you, a meta-analysis, and there are techniques to combining different studies with different sample sizes in a way that by combining them, you come up with a single result and you can make some sweeping conclusions. But one study alone doesn't do that. So we have to be very conservative with our statements. So we have found sufficient evidence to suggest that weight is less than 14. All right, so there's only a few of you here. Thanks for sticking around. Sorry for the mistakes today. I appreciate your patience. I don't know if I can edit them out, but maybe I'll try. Okay, have a good night, have a good weekend, and see you on Monday. We'll just continue. I'm going to focus Monday on the last thing I need to teach you about. Otherwise, these are just review problems for you, most of the notes, and techniques to solving problems. But the last thing I want to talk about are matched pairs tests. So if you remember in design of experiments in the first unit, we're coming full circle, and I'm going to teach you how to analyze the data from a matched pairs design. Just looking for that page. So you can be sure I will ask you a question on matched pairs. This stuff. I will ask you a question on this for next week's quiz on inference. It's known as the 2-sample t-test for matched pairs. Okay? So have a good night. Have a good weekend. See you Monday.